Hi, welcome back. This is the second um, video on Vector Operations 1. And again, it's taken from a PowerPoint presentation, which I would have done in class. And I'm hoping that this might be a little easier for everybody than the whiteboard. Don't forget that what I've done is I've created a PDF, which is exactly the slides that I'm showing you now. It's 4 per page. It's in color. You can download it. You can look at it. So one of the advantages, again, of doing taking the YouTube approach is that you can pause it and rewind it, so forth and so on, watching it any time. Because I know that, in these days, we got some not so great things that are going on in the world, and you can't always be available right at class time. So I'm hoping that this works out for us. All right, so this is where we left off last time. So we're basically working, I'm paralleling the textbook and the presentation there, and I'm trying to use many of the same examples from the textbook. This is section 10.4, and I'm trying to also use the notation in the textbook. Different books might have different ways of showing things, but this is kind of universal. Okay, so again, just here's where we ended up. Finding a vector, so V is the vector. Um, this symbolism here means the magnitude of the vector, which is the length of the vector. So you got a length, and I and j are the Kronecker vectors. So this is a scalar quantity. It's a multiplier. It stretches and shrinks vectors. Whereas over here, what we get is we get the angle or the tilt of a vector, or the direction. Okay, so I is the Kronecker vector, is the unit vector in the horizontal or x direction, and j is the Kronecker, the unit vector in the y direction. Okay, so let's do some examples. Now this is going to be a little bit tough, and we're going to have to follow along with pencil and paper. So if you have to pause the video and take a look and make some diagrams, that's to be expected, and that's what you can do here. Okay, so let's look at finding a vector given its magnitude and direction. A ball is thrown with an initial speed or velocity of 25 miles an hour in a direction that makes an angle of 30 degrees with the positive x-axis. Express the velocity vector in terms of I and j, and compute the initial speed in the horizontal direction and the vertical direction. All right, so direction in this case, a horizontal direction, vertical direction also mean components. So when you throw an object at an angle, it has a horizontal component and a vertical component. Okay, so let's see if we can work these out. Okay, so we're going to do it algebraically, following rules, and then we're going to look at some pictures, and hopefully as we mature in our understanding, we can think of both. All right, the magnitude of a vector. Magnitude in this case is given 25 miles an hour. We have an angle of 30 degrees. And the vector itself then is given by this definition, which we just went over. And in this case, the theta is 30 degrees. So we're going to work these out. Sine of 30, we all know, is a half. Cosine of 30, right, 3 over 2. We've done this many, 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 many times. Okay, so this right here, radical 3 over 2i plus 1 half j, corresponds to this part of the definition. And the 25 miles an hour is the magnitude. That's a scalar. We multiply it out, and this is what we get for the I and j components. Now, what does that mean in English? Well, I is associated with the horizontal component. So we have 25 radical 3 over 2, or approximately, this is similar for approximately now, 21.65 miles per hour in a horizontal direction. And the y component is 25 halves, or 12.5 miles per hour in the vertical component. So the j is the vertical component, and the I leads to the horizontal component. Notice the notation here. Vector V, x component, vector V, y component. Okay, moving along. Here's our picture. This was given. What was in pink here is given. So the magnitude was 25 miles an hour. That was the initial velocity of the ball. And the angle was 30 degrees. So what the question asks us, let's go back and look at the wording. Express, we want the x component and a y component of the velocity. Okay, so this is the y component, or the j, the unit vector j, and this is the x or the I component. And this is what we sort of figured out. And we're going to learn next time how to go in the other direction. But at any rate, this picture should align up in your mind with the computation we just did. Okay, let's look. Second example. Find the direction angle of a vector. Find the direction angle of the vector 4i minus 4j. Well, again, I'm a diagram guy. Okay, that's why I wasn't very good at foreign language, which was oral or auditory. I was better with, sight and visual. So 4i minus 4j, going to draw a diagram. Clearly, positive here and negative here puts me in quadrant 4. Okay, the initial point is 0, 0. The terminal point is 4, negative 4. This is our vector. Okay, so theta, the angle theta is y over x. Okay, so, whoops, I made a mistake here. This should be the arctan of negative 1. I'm sorry. Okay, so the arctan of negative 1. So I messed that. I left out the arctan here. I'll try to fix that and and repost it, but that's definitely a mistake. Okay, so you put this in your calculator, arctan of negative 1, and you end up with negative 45 degrees, which is the angle here. Now don't forget, that's principal value. What we want is the quadrant 3 angle, so the answer is 315 degrees. Okay, so that would be the direction of the vector. So just as a warning, when we use an inverse trig function, we're getting a principal value. So often what we have to do is go back to the physical situation and see what that implies. All right, so the answer here, theta, 315 degrees. Okay, now this is going to be a little more complicated. Two movers require a force, in this case magnitude, of 300 pounds to push a piano up a ramp inclined at an angle of 20 degrees from the horizontal. So here's our diagram. How much does the piano weigh? Well, okay, this is an example of something called mechanical advantage. Okay, so by having a ramp, we can get by with less effort or force, because otherwise, if we were simply lifting the piano up, the piano certainly weighs more than 300 pounds. So this is called a simple machine, and you study that in physics. What we're going to do is we're going to make force diagrams here. F1 is vertical. Gravity acts vertically from the center of the Earth, where we assume it's concentrated, to the surface of the Earth. So F1 is the force due to gravity, which is the weight of the piano, which is what we're looking for. Okay, F1 is perpendicular to the ramp, and it is the force that the mass of the weight of the piano exerts on the ramp. And, that's F3. And F2 here, as we can see, is the amount of effort needed to push the piano up the ramp. Okay, we have two triangles here. They're right triangles. They are similar. So this angle of 20 degrees corresponds to this angle here of 20 degrees. So triangle ABC is similar to triangle, let's see, that would be DBF. Okay, so let's look at our next line, and hopefully what I said is correct. From the diagram in blue, that's the vector force diagram. F1 was the weight of the piano. Due to gravity, that would be vertical. F2 is the force exerted by the movers along the incline ramp. Whoops. And as you can see, that would be 300 pounds. And F3 is the force which the piano exerts on the incline ramp. Okay, so looking at our diagram, whoops, went to the wrong page. Looking at our diagram here, we have 20 degrees, okay? And the sign of that is opposite over hypotenuse. So opposite is F2, hypotenuse is F1, which is what we're looking for. So we have opposite over hypotenuse, so we get that the sine of 20 is the magnitude of the, or the length, F force F vector F2 over vector F1. F2 is given as 300 pounds. F1 is the weight of the piano, which is what we're looking for. So therefore, we work this out. What we're going to do here is we're going to solve this. We want to solve for F1. So we cross multiply, and you get F1 is 300 over sine 20. So you get the piano weighs approximately 877 pounds. So we definitely get a mechanical advantage by using an inclined plane. This is one of the simple machines. Okay, look at another problem. Typical. We have a crate which weighs 1,200 pounds, is suspended by two cables, and the cables are here and here, okay, from the fixed ceiling at angles of 30 degrees and 45 degrees, as shown. Compute the tension, which is the magnitude, in each cable. Okay, so we have our basic diagram here, and what we're going to do now is we're going to create a force diagram. And the force diagram is represented by the vectors in blue. Okay, so the cable tensions are represented by the magnitudes of the blue force vectors F1 and F2, and the magnitude of the blue force vector F3, vertical again, represents the weight of the crate. So this 1,200 pounds right here, and gravity weight is always vertical. Okay, so what we're going to do is going to now work with this. And the next idea is we're going to compute the force vectors. Okay, so here's our definition. Okay, vector F1 is the magnitude times its direction. Vector F2 is the magnitude times its direction. And the easiest one is vector F3. The magnitude is 1,200 pounds, and it's negative directed down the J direction. Okay, so let's work these out. And the idea is in static equilibrium, static means at rest. In other words, we don't have motion. So the forces have to balance. The sum of the force vectors must equal 0. So when there is no motion, it means the force vectors are in balance. You have as much up as down, as much left as right, so forth and so on. So the sum of the force vectors must equal 0. So that's an important idea, and that's going to give us our equation, which we're going to solve in a little while. All right, so let's go back. Here's F1. Okay, and what we're going to do now is come up with a representation of that vector. Okay, now this is 30 degrees. That's in quadrant 2. So the actual angle here is 150. So that's where that comes from. So it's the magnitude, which we don't know. We're going to look for that. That's the tension in that cable. Cosine of 150, negative rad 3 over 2. It's in quadrant 2. Sine of 150 is positive in quadrant 2, is a 1/2. Similarly, you go back to F2. Now that's in quadrant 1. So the angle theta is 45. And we don't know the tension in that cable. That's the magnitude of F2, which is what we're looking for. Cosine and sine of 45 are both rad 2 over 2. Okay, so we're going to multiply this out. There we go. We're going to multiply this out. There we go. And we'll see why we have to multiply it out in a little while. So if you want to pause the video, take a few moments and verify that cosine of 150 is indeed negative rad 3 over 2, things of that nature. Okay, so we have f1, vector, vector f2, vector f3, and now we're going to go with this idea. Static means no movement, so everything has to be in balance. The ups, the downs, left, right, they're all going to be equal. Okay, so here we go. Applying the definition of static equilibrium. This is going to be a little tough. The sum of the force vectors must equal 0. So the force vectors are F1, F2, F3. They got to equal 0. Here's what that implies. Now we're going to write it in IJ form. We're going to write it using the unit vectors in the x, going to write it in unit vectors in the x and y direction. Okay, so this, if you go back to the previous line, this is F1. Go back to the previous line or the previous slide, this is F2. And right here is F3. So force one, vector 1 plus force vector 2 plus force vector 3 equals 0. When we write it out in component, in IJ component form, that gives us this. Now, let's look at this very carefully. Again, the idea in static equilibrium, both the coefficient of the unit vector I, that's the x, or the Kronecker vector in the x horizontal direction, and the coefficient of the unit vector j must equal 0, because that's what static means, no movement. So the i's are going to balance, the j's are going to balance. All right, here's what happens. I take all the I terms here and here, and they have to total up to 0. So I have negative rad 3 over 2 times the magnitude of F1 plus positive rad 2, plus positive rad 2 over 2 F, plus, let's start again with that. This term plus this term must equal 0. So all I did is I took out the i's. So I got negative rad 3 over 2 times the magnitude of vector F1 and rad 2 over 2 times the magnitude of F2. So that equals 0, and consequently the coefficients of the j, these three terms, must also equal 0. So we have a system of equations. Okay, so what we're going to do, well, you can probably guess we're going to solve this guy for F2. Okay, so we're going to work with the I part. I took out the I, and this coefficient has to be 0 because this has to be 0. This is a unit vector of length 1, so this has to equal 0. So I get this equals 0. I'm solving for F2. Well, what am I going to do? I'm going to multiply both sides by 2. I'm going to move this over. I'm going to divide by radical 2. So F2 is this crazy quotient times the magnitude of F1. Okay? And then what I'm going to do is I'm going to take the same thing, the j part. Let's go back there. Okay, so this equals 0. This is a vector, so this scalar quantity here must equal 0. That gives us our second equation. Okay, now I'm going to take this for F2 and substitute it right in there. I get this crazy thing. Okay, but at least I have now one equation and one unknown, which is the magnitude of F1. I'm going to do some razzle-dazzle. What am I going to do? I guess I'm going to cancel out the radical 2's here. I'm going to multiply everything by 2 and look at what I get. Okay, so let's go back. I multiply by 2. This becomes a 2400. I'm going to get it over to that side, and I have a 1 plus radical 3 times the quantity magnitude of F1. I solve for magnitude of F1. I get this expression. So the tension on cable F1, which is this magnitude, 878.5 pounds. And for F2, a little more complicated, but I just substitute this value in, 1075.9 pounds. Okay, so we just computed the magnitude or the tension on those cables. So I couldn't show all the little details here, but I want you to go through this pencil and paper, work it out, and I'm going to go back. I'm going to fix, what am I going to fix? I'm going to fix this here because that should be arctan and -1. Okay, so take a look at this, and this sort of ends up what we did with section 10.4, which is vector operations 1. So I hope it's helpful. If you combine this with the PDF, you can go step by step, you can pause, you can do anything you want. And we're going to pick up with section 10.5, which, got to tell you, interesting about the dot product, and we'll see that in our next video. Thank you and good day.